Good morning, everybody. There is still people coming in. Still, I suggest we get started. Welcome to our talk on IDPS evasion in the age of IPv6. My name is Enno. Over there is Antonius, and this is Raphael. Antonius and I, some while ago, we started building a lab for testing IPv6 security in various ways. At some point, Raphael joined us to write a thesis on the exact topic, and we made some, what we think, quite interesting observation when it comes to certain elements of IPv6, namely the extension headers, and how they interact with current security models, especially when it comes to IDPS and detection techniques, which can be, as we will show, circumvented. The agenda of our talk is quite simple. We will give some introduction on what those extension headers are, how they work, how they interact with fragmentation. We will give some overview of the lab we built, and of course we will have some results and some nice demos. We assume that most of you are to some degree familiar with IPv6. We further assume that you are aware that IPv6 is there right now. It's not no longer like, oh, this will happen at some day, if at all. These are the numbers from Belgium, the nice neighboring country. In Belgium, we have right now about 27% of users IPv6 enabled. So 27% of people can use IPv6 when accessing the internet. And this means this has been a part which was delayed for many years. There was a number of, say, content or services already IPv6 enabled. There was a number of carriers transporting it. But so far there was a lack of users, which has been cured in the, say, last 6 to 12 months to some degree. Even Greece, where Antonius lives, 3 months ago there was just 1% of IPv6 users, and then within 1 month it jumped to 5%. So IPv6 is there. IPv6 is there even if you think in your environment you don't have it. As probably some of you are aware, Windows comes with IPv6 by default enabled. Many other operating systems do the same in the interim. So you should expect IPv6 to be present either within your organization or at least to some degree coming from the internet to your premises. So talking about IPv6. Some of you might think, well, it's just IPv4 with longer address space. Actually, it isn't. It's fundamentally different in the way it works, on the network layer. And one of the main differences is a concept called extension headers, which have been within IPv6 from the very beginning. There is the main RFC 2460, which kind of marked the beginning of IPv6 specification. There were earlier ones, where 2460 is the main one. And that one has a huge section on these extension headers and how they work. And to give you a quick intro on that, an IPv6 datagram can be thought like a German train, trains in other countries too, obviously, but with wagons. And the number of wagons might not be clear when the train leaves the station. It might have changed once the train arrives somewhere. So it's composed of, let's say, elements. And these elements, actually, from a technical perspective, are headers which are inserted after what is in IPv6 parlor called the main header. Like in most network protocols, there's a header. The main difference, or a big difference now, being after this one, additional headers for specific purposes can be inserted, which right now there is even, say, 18 years after the initial specification of IPv6, there is not much practical use of these extension headers in actual, say, services or network protocols. But given they have been there from the beginning, given they have been there in the initial specification, every stack is assumed to support those. And every middle box, as it's called in IPv6 language, stuff like firewalls, IDPS, proxies, all these elements have to support them. Whereas supporting means, first of all, there is a number of, say, well-known extension headers. That's the one which can be seen here. Some of those will be covered in more detail later. Next to that, there might be new extension headers. And the RFC 2460 recommends a certain order of these extension headers once they are in a packet. And there is a recommendation that except for one that is the destination options header, they should occur mostly once. But it does not specify or recommend or whatever what happens if those recommendations are not followed. And some of you might know in the internet there is an old principle, an old law, the robustness principle or Postal's law, which we are big fans of in many aspects, both when it comes to networking and when it comes to real life. This robustness principle essentially says be conservative in what you send. Once you compose a packet, follow the specifications, but be liberal in what you accept. Once somebody else sends you a packet, well, allow some flexibility there as long as you have an idea what this packet is about, process it. And this robustness principle might play a certain role in when it comes to our findings. There is an RFC specifying how to, say, handle unknown extension headers. And that one essentially says, an intermediary node should forward packets with extension headers. And in case this intermediary node does not recognize an extension header, it is still expected to process it. So the overall attitude towards extension headers is, well, they can be there. And once you encounter them, try to process, try to understand. But in general, do not discard anything of that. Do your best when it comes to understanding and processing the potential contents of the headers.
So all this cause three problems. Problem number one, there are too many things that you can vary. For instance, you can vary the type. You can have destination options header, a hop-by-hop header, a fragment header, and so on, so on. There are about 9 extension headers up to now. Secondly, you can vary the size of them. Some of them have fixed size, about 16 bytes, but some of them can be as long as 2,000 bytes or even more. You can also vary the order. You can have the hop-by-hop, the destination options, the fragment header, or you can have the destination options and then the fragment header, and so on, so on. You can play with all these things. You can also vary the number that each header occurs in its chain. For instance, you can have one destination options header, you can have 2, 3, one routing header, 2, 3, and so on. Officially, okay, there is a recommendation that there should be just one for each one of them, except from destination options header, which should be just twice. But it's just a recommendation. It has been shown that most operating systems accept extension headers in any number of occurrences in the IPv6 header chain. And moreover, finally, you can vary the fields in there. Some of them, like the destination options header and the hop-by-hop header, have some options. These are in the format of type length value, so they can significantly vary from header to header. To sum up, this is a kind, the IPv6 chain is something like a function which has too many variables, so you can vary too many things, and varying so many things, you never know what the final outcome will be. Problem number 2, fragmentation. Fragmentation was quite simple in IPv4. we had just the main header, the IPv4 header, and then layer 4. Here it's slightly more complicated because we have the unfragmentable part, and the unfragmentable part can consist of the IPv6 main header plus some of the extension headers, the ones that must be processed en route to destination. And we also have a fragmentable part. The fragmentable part consists of the rest of the headers that should be processed just from the end node, plus, of course, the layer 4 header, plus the final payload. So when we fragment this initial IPv6 datagram, the unfragmentable part remains constant, but I remind you that it can have one or more extension headers. Then we add the fragment header, which takes place in order to perform the fragmentation. And finally, we have the fragments of the fragmentable part. The third problem is how these extension headers are chained. Let's take an example here. We have a main header, the IPv6 main header. We have a routing header, destination options header, and TCP header plus payload. Each extension header has a value, has a protocol value. We all know that the protocol value of IPv4 is 4, or of IPv6 is 41. So, for instance, the routing header has a protocol value of 43. The destination options header has a protocol value of 60. TCP has a protocol value of 6, well known from the IPv4 era. So, each header, both the main one and the extension headers one, have a field called next header value field. And this field points to the next header. In our example, IPv6 header has a next header value equals to 43 because it points here, to the routing header. The routing extension header has a next header value equals to 60, which points to destination options header, and so on. This is how they are chained. It's a kind of a pointers concept. So far, so good. No big deal. I mean, that it's pretty easy. So what's the problem with this? The problem comes when all these chains are fragmented. Let's take again an example. Let's assume that the fragmentable part is the one displayed on the slide. I have a destination options header, which points correctly to the TCP header, whose protocol value is 6. And then I have the TCP payload. And let's fragment this one into fragments. Let's assume that part 1 is just the destination options header, and part 2 of the fragmentable part is the TCP header plus the payload. Now I have a question. What should be this next header value of the fragment header in the first fragment? I remind you that the next header value, the protocol value of destination options is 60, and the TCP is 6. So what should be here?
Any suggestions?
Excuse me? 60, correct? 60, absolutely, yep. So the fragment header points to the destination options header. Now the second fragment. I have here the TCP header. What this next header value should be? The TCP header has a protocol value of 6. Is it obvious? Any
Intuitively,
suggestions?
one might think it should be 6, but actually,
But actually it's 60. Although at first, we may assume that it should be 6 because this must point to TCP header. Actually it should be 60 because the fragment header should always point to the first extension header of the fragmentable part. And who is going to point to the TCP header? The destination options one. This is a really minor detail, but as we will show later, we will exploit this detail in order to evade a high-end commercial IDPS device.
so overall, it's a kind of mess. There is a huge variation of different parts of a potential packet, or when it comes to the size, to the order of things contained there, of the options within the headers, and all this, which then again, as some of you might already figure, poses problems to security enforcement modules, which are supposed to act on identifying stuff and identifying like boundaries within packets and contents. Once you throw in a huge cloudy mess into such a device, this might cause all types of problems. especially because all these things can combine in any potential way. There is just very few restrictions, like there can only be one hop-by-hop header, that is a certain type, and that one has to follow the main header immediately. But besides that, there is pretty much no restrictions on how to order, combine, fragment all the stuff, which clearly shows, some of you might be familiar with the LangSec initiative, and within LangSec, one of the most basic rules is whenever you pass something, write a grammar before, like parsing, well, which clearly hasn't happened in the IPv6 space, which then again causes problems. Too much freedom and flexibility, which is inversely proportional to security, and can lead to, let's say, a certain chaos. To get more practical, what could actually go wrong? Now figure that right now in most environments, security enforcement like to decide if a packet is a good or a bad one, or it should go this direction or another one, or be null routed, whatever. This decision is taken upon identifying packet content, and well, then the question comes up, what if we try to circumvent this identification? What if we try to confuse security enforcement modules of different types? Actually, we did a number of firewall tests as well, but the most interesting ones were the IDPS ones. In theory, this type of problems has been discussed for many years, but this was just theory. Nowadays, Antonius wrote a nice tool which is freely available called KRON. And KRON can, as you will see later on, implement all these techniques by simple command line switches. Easy to use, easy to create packets which have all these combinations in various ways. And it can even be used as a proxy. So you throw in some whatever type of attack or scanning traffic, like run Nessus, run it through KRON, and out comes from KRON all the traffic in heavily, I wouldn't say obfuscated, but prepared way. Actually, we built, as I said, we built a lab. This lab consisted of 4 IDPS solutions, 2 open source ones, Snort and Suricata, 2 commercial ones. This is the tipping point we use. This is the SourceFire device. Both are medium-sized enterprise devices. I mean, it's not the biggest devices you might find in corporate environments. Still, on the other hand, this is not Soho stuff. This is stuff that you can expect, can reasonably expect to sit in, say, medium-sized organizations or even large organizations, and serving as protecting entities or entities identifying and trying to block the bad network traffic. Overall, so far, we have found 12 different evasion techniques. All of them were reported to the respective vendors, and all of them were new at the time of us finding them. They were reported. Some of them were patched. Some of them were patched very quickly. Some of them were patched with a certain delay. But actually, in the case, as you will see later, in the case of Snort and SourceFire, there was a, well, say, interesting way how they acted upon this. They had a kind of, we don't have time to take care of this, go through customer support attitude, which is particularly interesting. As some of you might know, we have been given a number of Black Hat talks before, especially covering Cisco stuff and breaking Cisco stuff and disclosing vulnerabilities in Cisco stuff. At the time, there was always good communication. I even recall Black Hat 2010 when Antonius first gave his talk. It was 2011. Okay. Antonius first showed the results of him analyzing the operating system behavior when it comes to fragments and extension headers, and I And another guy gave a talk on Cisco Voice over IP. And there we had even a guy from Cisco PSOT sitting in the room, Gauss, and discussing the stuff with us. Nowadays, it seems times have changed in that space. Anyhow, let's have a closer look at the actual stuff you have probably been waiting for.
Yeah. Let's begin with Suricata. Suricata, as you know, it's an open source project. It has been funded by the US Homeland Security. During our tests, we tested several versions. We started with version 2.0.1. Each time we found a vulnerability, I used to report it to the developers. They used to patch it, and so then we test the next version, 2.0.2. We waited again, 2.0.3, waited again. And so up to now, we have found at least, I would say, 6 different evasion techniques. And we're going to demonstrate the latest one against 2.0.3. This is how the evasion looks like. We are going to use 2 fragments. First of all, for our purposes, Suricata has been installed in a virtual environment. And it is in a passive mode, meaning that it captures the traffic, it triggers alert, but it doesn't block it. We used, of course, 2 parts, a fragmentable part and a fragmentable one. The unfragmentable part consists of a type 0 routing header, and of course the main header. And the fragmentable part just from the destination options header on layer 4. In the first fragment, we include the destination options header, and the second, the layer 4 header. But it's time for some action now.
Okay, now we will demonstrate this. I will just send a simple ping command, ping request with Chiron to our target to see here in our log. Oh, sorry. Our simple alert is showing up, an IPv6 Azure request is sent. In Wireshark, we see our request and our reply. So now let's reset this thing. And now I send our founded combination. We see in Wireshark it is fragmented, first fragment, and the complete message. So here we have our routing header, our fragment, and in the next fragment we see in the first fragment just the destination option header, and in the second fragment the ICMP and payload. And as we see in Suricata, no alert is showing up.
So the packet gets through, but Suricata doesn't notice anything, as it's not able to pass these, the set combination of fragmentation and extension headers in a correct way.
The goal here, we wanted to simulate, let's say, a kind of exploit. So for this purpose here, we used a simple ICMP-v6 echo request. We enable a rule that detects simple ping. This was a goal, to send a simple ping without being detected. Okay, as we said, we reported all the problems, and we were impressed actually by the speed that Suricata developers patched all of them. It didn't take them more than a week in order to patch it and release a new tool. This is the latest one now, 2.0.4, which has fixed all the vulnerabilities that we have discovered and reported to the Suricata developers. Okay, now we're going to talk probably for the most sophisticated of the attacks. This is used against tipping point. Again, we have 2 different cases here. This is the first case. We found it back in March of 2014. Let's assume that we have this fragmentable part. We have a destination options header, TCP and the payload. And this is how we managed to evade tipping point at the very first time. If you recall, this next header value from the introduction should be 60. We found out that when this one is 6 and the first one is 60, tipping point does not trigger any alert. Tipping point does not block our packets. So this was a way to evade tipping point. This was back in March. We reported this problem to the vendor. They fixed it after 3 times, if I recall correctly. but again, we have the second one. Before proceeding to the second one, let's see how this technique works. And what's the difference here between 6 and 60? Okay, this is a Warsack output of the pre-described technique. The yellow area here is actually the TCP packet, the TCP header, plus the payload. In our example, it's a kind of XSS attack. The red one is the destination options header. If you see here, the yellow circle, it's the number 50. Number 50 is the hexadecimal of number 80, which is the HTTP port. In our example, we tried to evade TCP and actually to launch a kind of XSS attack. The problem is that due to the next header value of 6, both Wireshark and Tipping Point assume that the TCP header, instead of starting here, it starts over here. So instead of looking for the TCP port here, which is 80, it tries to find it somewhere here, which is 0100. But 0100, as you know, in hexadecimal, it's 256 in decimal. So it believes that the packet is going to this port in 256 and not to port 80. So the signature is not triggered. As I said, we report the problem. The vendor reacted. Okay, not that fast, but it patched the problem. But again, we found another way. This is the old technique that I described. First fragment, second fragment. And when it was patched, we said, okay, let's try it again. We launched exactly the same technique. And we noticed that the first fragment passes through the device while the second one is blocked. Now, what you would do in our case, you observe that the patched one allows the first fragment and the second one is blocked. Any suggestions?
Any hacker mindset? What could you do if you notice something gets through and something is blocked?
Sometimes things are more simple than you expect.
It is quite simple, actually.
You can just send the second fragment once more. So the first time it is blocked, but the second time it passes through. Yeah. Okay, we have a nice demo here. Again, time some for action.
To show that demo, I will use Wireshark on my side. It should be running. Well,
we're going to show both the attacker's machine and the defender's machine. You are going to see that the attacker sends 3 packets, 3 fragments. The one is blocked, and the target receives just the 2 of them, which are more than enough to trigger a response.
So,
okay. So now I will first send just a simple packet again to see what has happened. And we see in my Wireshark the request is sent. And here I have the log of the tipping point, and here we see, okay, one package is blocked. So it just simply blocked my packet.
And I don't see anything. There's nothing comes in here. Let's assume this is the destination system where the traffic is destined to.
Yeah. So now I will send our found combination. So you see here, first fragment, second fragment, Wireshark reassembled it since now. And here we see the third fragment, which is simply the second one again. And if we look in the log, and I refresh the log, we see, okay, he blocks one. But if we now switch to our target, and even though we see it in my Wireshark, we got a reset back.
Well, I find the reset is sent because there was nothing listening on the target's machine on port 80. The main point being now with the second try, something got through, which can be seen here. Actually, it's 2 packets arriving on the destination system, which is sitting behind the tipping point, which is protected by the tipping point. Still something gets through. Well, in the end of the day, I sent back a reset, but the interesting parts are the first 2 ones. Again, note, he sent out 3 Here it's only 2 showing up. It's like an, Mad Max 3 Thunderdome. It's a variation, not 2 go in, 1 gets out, but 3 go in and 2 get out. And you can see here again, here is a fragmentation header, here is destination options, and it's split into 2 fragments, which contain even the payload. You can see down there which were sent, just to indicate any type of payload gets through, even though this packet should have been blocked by the tipping point device. And actually, without those, say, fiddling around with the packet, it was blocked. It's just the same packet as in the first try, but now it's crafted in a certain way.
Okay. So let's come to Cisco and SourceFire and Snort. I won't hand over to Eno again, but before doing so, just to mention that we could expect that these 2 IDPS systems should have a quite similar behavior, because as you all know, SourceFire is based on Snort. So we wouldn't expect any differences, but we found out that some 0 days working against SourceFire didn't work against Snort.
Yeah, thanks. I'll head back and give back to you in a second. The main point is here, given I was kind of supervising the lab, I was involved in the vendor communication in all these cases. And as I said, we already in June, we contacted Snort developers, sent PCAPs. We didn't get any response. We reported into SourceFire in September. Actually into different people, given we are involved in customer projects, including SourceFire. We we had at the time and still have certain channels into SourceFire, and that was a quite disappointing experience. They got back to us like, "Oh wait, what is this? Don't waste our time. Why are you contacting us?" And actually, they suggested going through customer support. So clearly, at least those persons we were talking to did not realize what this was about, which was surprising to say the least. I mean, we understand that after the acquisition of SourceFire by Cisco, there's all types of reorgs and things going on, and people might be busy, but this again was interesting. If responsible, or as they say nowadays, coordinated disclosure fails, what is left for the researcher? Go with full disclosure, which is exactly what we are doing here and right now.
Okay. Let's describe our live demos. First of all, we're going to test SourceFire. It's the latest one. It's the device up here. This is the model, the version, and the build. We must mention here that both Snort and SourceFire have some IPv6 rule in decoders preprocessor rule that are not enabled by default. Without enabling them, evasion is even more easier. It's really easy to evade it. So we try to make it more difficult for us. We try to, let's say, enable all the rules related to IPv6, as long as, of course, they don't trigger any false alarm, because there are a couple of them that they trigger false alarm, even in full legitimate traffic. So enable all these rules. You can see the signature IDs here, which actually do a pretty good job, but still, as you will show, there are ways to evade it. So, talking about SourceFire first. This is one example how SourceFire can be evaded. Again, we have 2 fragments, our favorite combination. In the fragmentable part, except from the main header, of course, we use 3 destination options header. In the fragmentable part, we have just 1 destination options header in the first fragment, and another one in the second fragment, plus, of course, the layer 4 header. So now Rafael is going to demonstrate how this combination can be used to evade SourceFire. We're going to send these 2 fragments, and we're going to show that the target receives these two fragments and responds to them.
Okay. Now, same procedure as before. I would just send a simple, and this time again, a ping request, and we see it show up in my Wireshark. And if we refresh the log of the source file, we see even here it is shown up in our log and is blocked. So I now will clear the block again. Yes. And now I will send our combination. We see here 2 fragments, ping requests got through, and we should normally see.
Take a look at the target system. I mean, it didn't show that before nothing got through, but you saw it in the alert being triggered. And now this is the final destination of the packets. Again, we see there's something getting through. The ICMP packet, which should have been blocked, or just should have triggered something. Gets through. I reply on that one, and looking a bit closer, it can be seen there is again, as Antonius laid out, there is a number of destination headers which shouldn't be there, say if it was production traffic. There is a fragmentation header, and this gets. The Wireshark has some difficulties in correctly. Say, not parsing, but understanding or interpreting the packet. But as you can see, it gets reassembled on the final point and is processed normally without triggering anything.
Just a note here that both tipping point and source file are in line. So not only they should trigger an alert, but they should completely block the traffic. The reason that you see the traffic at the target is more than enough to show that source fire, in this case, and the big point before had been evaded. Okay, this was about source fire. Surprisingly enough, this technique does not work against Nord, I suppose because source fire is based on 2.9.6 version of Snort, and the latest Nord version is 2.9.6.2. So we tried to find something for Snort too. We used the latest version, the one that I mentioned, 2.9.6.2. Again, we enabled all the IPv6 related rules that do not trigger any kind of false alarm and tried to evade it. Snort has been installed in a virtual machine in Rafael's laptop. It is configured in passive mode, so we will show the alerts over there. And this is how the technique actually works. Here, the interesting thing is that actually this combination can be more or less a fully legitimate packet. In the previous example, we had 3 destination options header in the unfragmentable part, which should not be the case. According to the RFC, there should, not must, but should be just 1 destination options header in the fragmentable part. And we used 3. A kind of violation, or we didn't follow, let's say, the recommendation. Here, we use an almost fully legitimate packet. We have a hop-by-hop header following directly the main header, as it must does. We have a routing header. We use type 3 because type 0 has been deprecated, and thankfully Snort triggers an alert for that, so we use type 3. And a destination options header, all of them in the fragmentable part. Then we have our fragment header, and then you use another 1 destination options header in the fragmentable part, layer 4, and the payload. I would like to remind you that having a destination options header in the fragmentable part and another one in the fragmentable part is fully legitimate according to the RFC. So this could be a fully legitimate IPv6 packet in the real world. And this combination can be used to evade Snort. Okay, Rafael, you're there?
Yeah, same again. We'll just send a simple just a simple ping request. See my echo reply. We see the alert in our log above. And now clear the log a little bit, so you see that there's nothing showing up. And now I will send our founded combination. You see here again fragment 1, fragment 2. I will reply and nothing appears in the log. And if we're looking at our sended packet, we will see here our hop-by-hop header, our routing header type 3, our destination option header, and then we come to the fragmentation. Fragmentation part 1 is just the destination option header, and the fragmentation part 2 is again the ICMP v6 and the payload. So as you see, nothing in the log, reply got back.
So it's fully processed by the final point of the packets, which is the main message. Just by adding headers in a certain combination, you get through to the final destination. And given Postal's principle, be liberal in what you accept, pretty much all operating systems will happily process those packets and act upon of them as if they were sent without any headers. So obviously this brings up the question, what could be done against this stuff? If you run IDPS systems, you should expect, or you certainly expect, they detect well-known bad stuff, which they clearly, as we have shown, don't once crafted packets are sent. What could be done? And this, we would like to differentiate between different parties involved in the overall process. Given we deal with IPv6 a lot, we are aware there is actually there's hundreds of RFCs covering IPv6 in some way, some of them even contradicting each other, some of them issued by interested parties or based on certain politics going on in IETF space. Still, when it comes to the main elements, there's a huge degree of ambiguity. Reading RFCs and then implementing stacks upon or based on these RFCs is a difficult task for a developer, as the RFCs and even the main ones are not always very clear. So there must be, we think, and again, we are aware of the way IETF works, and we are big fans of the robustness principle in general. Still, there is not enough, as we think, guidance or clear guidance when it comes how to process and how to actually build and act upon packets. Second, when it comes to Windows, we had the impression that, say, quality assurance or security quality assurance, there is room for improvement in Windows space when it comes to IPv6. Tools are available. Kron can be downloaded. We sent a number of PCAPs. Actually, we got from some of the, especially in Suricata space, we got very positive response, like thanks for the PCAPs and thanks for the tools, so we can test all this on our own. Kron has been released in the first version like 9 months ago or so. So it's not like it's a tool which is coming from nowhere. Security quality assurance in Windows space could be improved. When it comes to, say, your organizations, assuming that many of you are not involved in Windows space, but in like user space to some degree, in corporations or agencies using these devices, it should be noted there is a quite new RFC 7112, which specifies that an intermediary system, like an IDPS, like a firewall, or as they call it in RFC space, any type of middle box, is potentially allowed to discard packets once the full header chain is not included in the first fragment. which is a good thing, as header chain being fragmented, being split into several fragments. We don't see any cases, and we do a lot of IPv6 work, we don't see any cases where this should ever happen in production traffic. So allowing middle boxes to, you may throw this away if you can't recognize the full header chain within the first fragment, is a good idea. Still, some of our attacks would have worked nevertheless, like the tipping point one. That would have worked even if that the device acted like the RFC 7112 kind of allows. This is a deviation from the old mantra, like everything in extension header space must be fully processed, and regardless if it's fragmented or not. Secondly, when it comes to configuring security devices, there is two potential approaches. First, you might say configure filtering devices in a way that they drop all extension setters which are not needed, which immediately brings up the question, what are those? It's pretty much all of them, except for maybe in case you expect fragmented traffic, which shouldn't happen, but there are corner cases with tunnel traffic or DNSSEC where fragmented packets may actually show up. So what we think, we are not fully, we have different opinions here, Antonius and I. At least I think you should, it's fairly safe to drop pretty much anything, all extension headers, except for maybe fragment header, in case there's fragmented traffic, and obviously authentication and ESP encrypting security payload, the headers which are needed for IPsec. So running VPN traffic through a filtering device, then you would need those extension headers. But I usually recommend going with a very strict way, drop all this crap at the borders, or at least in case you want an IDPS to fully function the way that you expect it. The traffic has to be sanitized or scrubbed before it enters the IDPS. I do not expect that the problems or the types of problems that we have seen can be cured in a short term. Like it's, okay, they can be patched. And then once again, say several weeks later, or in some cases just days later, Raphael or Antonius or somebody else using Kron finds new techniques. I think this is a kind of unsolvable problem for IDPS. So if IDPS should function properly, sanitize the traffic before going into it. If you ask, okay, what is the actual practice out there? You might look at this default behavior of Checkpoint, for example, is they by default Checkpoint drops all extension headers, which does not include authentication and ESP, the ones for IPsec. But all others are dropped by default by Checkpoint. I think this is a good stance. I mean, it's obviously against, say, the spirit of the RFCs, allowing for flexibility. In Checkpoint space, you can only modify this behavior, like allowing them by editing table.dev, which those of you who are aware of Checkpoint operations, this is probably not the step one likes to perform in production environments. And there is no way of enabling extension headers in a GUI or something. It's just they are blocked, and the say typical administrator has no ways of enabling them. That's probably, I think this is by decision, by design decision. So it can be avoided, like people calling up, oh, your firewall, does it block anything? Could you please enable it? This just can't happen as long as you don't touch table dev. So they have a very strict filtering approach, which I think is a good idea. The second, as I said, if an IDPS should function properly, traffic must be somewhat scrubbed or sanitized before entering it, so it can be processed correctly. Do you want to add Anything from your perspective?
Regarding dropping exception headers?
Yes.
Okay, it could be a safe policy for the time being, but exception headers are here to provide some additional functionality that we may require it. For example, there are cases that hop-by-hop header is used in the local link for the router alert option. This can be the case even in the core networks. So there are some exceptions. IPsec is another one. And according to 7112, in the IPsec case, you also allowed to have the layer 4 header in the second fragment. So it's not that an easy, let's say, approach. Of course, if we don't use them, drop them. That's pretty straightforward for me. But if you're going to need something, then the problem starts to be kind of complicated.
Yeah, in general, I think drop them all. And I even think in IETF space, extension headers should be deprecated at some point of time, which shouldn't be too distant in the future. Besides all the technical, say, info we provided, we would like to remind and encourage all of you that both from a security researcher's perspective, IPv6 is a quite interesting protocol. There's many gray areas, there's many RFCs and sub-protocols and stuff nobody has looked on so far. And when it comes like to practical implementation, given we said it's there, it will haunt you in the next 5, 10, 20 years. Building a lab, finding out how actual devices behave, how operating systems behave is from what we think a crucial step in any type of well-planned and prepared IPv6 deployment. That's it. Thanks for listening. Enjoy Black Hat, second day. We should have like 10 minutes for questions.
Yeah. Just a small note, there is a white paper. It will be published in the Black Hat website. There is an appendix there, in Appendix B. There you can find all the command lines that we used in order to evade these devices. Here you can easily download Chiron and reproduce these cases in your environment if you wish.
Any questions? We have like planned for, well, yeah, 5 to 10 minutes. If there is questions, let us know.
You said that most operating systems will actually process this packet. Can you be more specific?
Yeah. The question was if, regarding the statement that most operating systems process such crafted packets, if we can be more specific, yes, we can.
Yeah. Actually, first of all, it depends on the combination. We have found out that different combinations trigger responses from different operating systems. So we cannot say it is just Linux or it is just FreeBSD or OpenBSD. But there was a paper published in 2012 in Black Hat Abu Dhabi, where there is a nice table there that summarized the result. There was another presentation at the Troopers Conference that was in 2013, in March of 2013, which updates this result. So if you download these talks, you will find a pretty good summary. I'm sure that I cannot give a clear answer right now because it exactly depends on the case. We examined there are more than 10 different cases, and we found out that in some cases, for example, OpenBSD responded, and some other Windows responded. So it depends on the combination, actually.
But in general, I think one could state that the most robust implementation is FreeBSD.
FreeBSD, exactly. FreeBSD was the most robust one.
Which did not, so most robust one means...
means that it doesn't accept too many combinations.
Obviously
of
bad combinations.
Extension headers that do not follow the recommendation.
But Antonius has done a lot of research in that space, and he has detailed results like these are the test cases and these are the responses of like 10 different. We had FreeBSD, OpenBSD, many Windows versions, Linux,
many Linux
several
versions,
kernels.
yes. Even Mac OS X, which resembles very much FreeBSD 8, if I recall correctly.
So it can be found, it just depends on the actual case.
And to be honest, when we do our tests and to try to find an evasion technique, you also try to find out which operating system responds to them, because you want to find the evasion technique that works in most of them, if possible.
Any more questions? I did not get a question. Sorry for that. Not a problem.
Thanks. In your testing, did you find any vendors that did this handle this correctly? This IPv extensions?
No. That was a very good and interesting question. The question was if, I mean, you certainly heard it, if we found any positive examples, like we just pointed out the, say, negative ones. This were the 4 that we actually tested. So in each of them, we found issues. And as I stated, I personally think this is a kind of unsolvable problem, as there's too many variations. Which with look at a certain offset of a packet and do so maybe even hardware like in ASICs. This can't work once you have that cloudy space of combinations.
I believe it's a problem of must against should. If you are more strict, if you have must there, this must first, this must second, so on, then it may be solved.
Yeah, at some time. Right now, we don't have any positive samples.
Regarding firewalls, by the way, if you wonder about the firewalls, we didn't mention anything about the firewalls, although there are some comments on the paper. It's not the fact that firewalls are better than IDPS devices. It's actually because firewalls, by default, usually use a default deny rule. This is what it saves, let's say, them. If you change the rule and you use a default allow and try to blacklist some traffic, then they face the same problems. So it's the kind of the different philosophy that we use in the firewalls that saves the situation.
There's another question over there. Right now, there is no such devices. But it might be that actually a very good question. Given we mentioned that architectural approach, if you want an IDPS to function properly, scrub the traffic before it enters the IDPS. This brings up the question the gentleman asked, is there any devices which can perform the scrubbing? Right now, there is none that we are aware of. We would expect that at some point, certain types of middle boxes might be able to perform this task to allow for further reasonable processing. But right now, no. Thanks again, and have a good day.